All right, so these are the important considerations when trying to improve or control the growth of a microbe. We've already discussed nutrients, so let's move on to temperature. Why would temperature, you know why nutrients are important to microbes. Why is temperature important, and how does that affect microbial growth? Well, not all microbes enjoy the same temperatures. Every microbe has a different optimum temperature for growth, but we do have a few broad classifications. Mesophiles like mild or moderate temperatures. Psychrophiles, there's psychrophiles and psychotrophs, which have slightly different temperature ranges. I just think about just collectively call these psychrophiles. Psychrophiles like it cold, thermophiles like it hot. There's a couple kinds of thermophiles, there's a couple kinds of psychrophiles, just lump them together. Psychrophiles like it cold, mesophiles like it moderate, thermophiles like it hot. This is sort of like the Goldilocks of microbes, right? This is like the oatmeal story in the Three Bears. All right, so what anatomical features or physiological features are affected by heat? Well, the main thing is going to be plasma membranes and enzymes. All molecules and all chemical reactions are affected by temperature, but these are particularly important cell elements when considering temperature changes. These are the plasma membrane and enzymes are going to be the first molecules to be impacted by the temperature of the environment. Let me remind you real quick what heat is. Heat is a kind of energy, right? It's thermal energy. And what thermal energy is it's a measure of the molecular movement. So it's actually a kind of kinetic energy. So when something has a lot of thermal energy, it means the molecules are moving really fast. So in hot air, the air molecules are moving super fast. In hot water, the water molecules are moving super fast. In a hot pan, the metal molecules are vibrating really fast. And that molecular movement, if those molecules are moving fast enough, they can cause damage to other things. They can cause damage to your skin. And that's because of the molecules colliding at high speed with the molecules in your skin. Temperature is how we measure thermal energy. Temperature is a measure of molecular energy or molecular movement. So whether you're measuring in Celsius or Fahrenheit or Kelvin, the number that you're getting is telling you something about how fast those molecules are moving. Now, when we're talking about chemical reactions in the cell, and when we're talking about how heat affects the cell, you have to think about how heat is affecting collisions between molecules. So where would more collisions occur? In a mosh pit or in a room with students sitting politely? Well, obviously, the mosh pit with a lot of movement and a lot of collision, with a lot of movement has a lot more collisions. The people in the mosh pit are really energized, just like the molecules in hot water. A classroom of students that are sitting politely at their desks, that's less energized in terms of kinetic energy, like molecules in cold water that are standing still. If one of you were an enzyme and another of you were a substrate and you needed to collide, let's just say we're taking a class of students, this whole class of students, and let's make it a face-to-face class actually to make this analogy work better. So if you were in a face-to-face class sitting at desks, and one of the students in the class was an enzyme, and another student in the class was the substrate for that enzyme, and the substrate and the enzyme needed to collide in order for the enzyme to work upon the substrate and convert it into a product. Would that collision between you be more likely to happen if you're sitting politely at your desks, or if you turned the classroom into a mosh pit? Well, it would be the mosh pit, right? So as you heat up the cell, collisions are happening faster and faster, and that's going to make reactions happen faster and faster between enzymes and substrate, right, until you get to denaturation. Now, heat also affects, for much the same reason, heat also affects whether lipids are solid or whether they've melted, because that depends on the energy in the molecules. More energy, more thermal energy in the molecules means the molecules are moving more. So if you put energy into a lipid like cocoa solids in chocolate or butter, if you put thermal energy into it, it melts. And that's because those molecules that were sitting nicely, like students at their desks, they were sitting still and nice before, politely. Now you've added this thermal energy and they start colliding, they start moving past each other, they start tumbling over each other, those lipid molecules, and that turns them into a liquid. But if you take that thermal energy away, all the molecules settle and they sit still. Now you've got a solid. So liquids are where molecules are tumbling past each other. Solids are where they're all still. Okay. You add thermal energy, you're going to get a liquid. You take the energy away, you get a solid. All lipids can be solid or liquid depending on their temperature. Olive oil, it's liquid at room temperature, but you put it in the fridge, it will solidify. Right? Butter is solid at room temperature, but you put it on the stove and it will liquefy, right? So different lipids, depending on their chemical structure, they'll be solid or liquid at different temperatures, but all of them, regardless of the lipid you're talking about, you invest energy, it's going to liquefy. You take the energy away, it's going to solidify. All right, so let's apply this more directly to the cell. So when cold, enzymes don't work well. And that has to do with that collision theory we were talking about with the mosh pit versus the students in the classroom. An enzyme has to collide with its substrate in order to cause a reaction and convert the substrate into a product, right? And so the more often you get more collisions in hotter temperatures, so the enzyme will work faster. It'll collide with its substrate faster and convert it into products faster in hotter temperatures. So as heat increases, enzyme activity increases up to a point. But then if you add too much energy, it's going to energize the bonds, these molecules inside the enzyme until the bonds are broken. So like I said, when you add heat, it's going to cause these molecules to vibrate and move more quickly. Now, up to a certain point, there are covalent and ionic bonds that are withstanding that addition of energy and maintaining the structure of this enzyme. But if you add too much energy, these ionic bonds are going to break. The enzyme's going to denature. So basically, the enzyme has melted now, and now it's non-functional. So enzymes work better as you increase the heat up to a point, and then they denature. Okay, so what happens when a cell gets too hot? Well, you remember the plasma membrane. Well, one thing that's going to happen is you're going to denature the enzyme. So if a cell gets too hot, the enzymes are going to denature, the proteins will denature, it's going to stop working. All the proteins will stop functioning. So you're not going to get the biochemical reactions that are necessary to sustain life once the enzymes have broken down. So that's going to kill the cell. Another thing that happens is you're going to melt the plasma membrane, because remember, the plasma membrane is a lipid. So it's going to, the plasma membrane is a lipid, and it needs to be fluid, but it needs to retain some integrity, right? It needs to have some structural integrity. So it needs to have that fluid quality, that dynamic quality that allows the cell to move, that allows proteins that are embedded in the cell membrane to move around and interact with each other. But it can't be so liquid that the whole thing just disintegrates, because it's floating in water, remember. So you don't want it to just disintegrate. So again, if a cell gets too hot, it needs to be in this Goldilocks region. If it gets too hot, the whole cell membrane is going to disintegrate and fall apart. Okay. If it gets too cold, the plasma membrane is going to solidify. And that is not good, because we've talked about how that dynamic liquid quality to the plasma membrane is essential to life. The cell needs to be able to move, right? So it needs to be able to endo and exocytose. The cell, the organelles that are made out of the plasma membrane inside the cell have to be able to function properly. The cell, it needs to be able to, the proteins on the surface of the cell have to be able to move around like ships across an ocean and interact with each other in order to function properly. So if you make the cell membrane rigid, like a cold stick of butter, it is not going to work. And that's going to kill the cell. Right? So if the cell gets too cold, the cell membrane will solidify, and it'll also slow down molecules so that the enzymes don't collide with their substrates very frequently. If the enzymes aren't encountering their substrates frequently enough to turn them into products fast enough to sustain the cell, then the cell will die. So basically, as things slow down, biochemical reactions that are keeping the cell alive start to slow down into really slow motion until they might halt completely if you freeze them completely. right? And again, that has to do with collision theory. So the two things that, to summarize, the two things that are most important for temperature in terms of, the anatomical features that are most affected by temperature are the plasma membrane and enzymes. They need to be in a Goldilocks region because the plasma membrane has to be liquid, but it has to also maintain some structural integrity. It shouldn't be so liquid that it disintegrates entirely. And the enzymes, for them to function properly, they have to be warm enough to collide with their substrates. They have to be moving enough and warm enough to collide with their substrates, but not so hot that they fall apart, that they denature. Okay. Now, the reason there are different, the reason we have psychrophiles, mesophiles, and thermophiles is because that sweet spot, that Goldilocks region, is going to be a different temperature for different microbes. And that has to do with what are the lipids that make up the cell, the plasma membrane, and how are the enzymes structured? Some enzymes are structured to function perfectly at colder temperatures. If you brought them up to room temperature, they would denature. And that's going to be a psychrophile. A psychrophile, you bring it up to room temperature, its enzymes denature. Its enzymes are structured to work fast at very low temperatures, but the trade-off is they're going to disintegrate at what we consider normal temperatures, right? So psychrophiles cannot tolerate room temperature. They need it cold. Their enzymes are dynamic enough to be able to work even in cold water where things aren't moving very quickly. But if they get too warmed up, they're going to denature at just room temperature. They're the lipid membranes. So their lipid membranes are going to be something more like olive oil, which is going to be, it's going to be liquid. It's going to take a much colder temperature to cause them to solidify, and they might be much, much too liquidy at room temperature. They might lose their structural integrity at room temperature, right? And a thermophile is going to have enzymes that will not denature, even at boiling point, perhaps. Here's a really good thermophile. This thermophile can exist above the boiling point of water. Right? So its ideal temperature is right about boiling point of water. So those enzymes are structured in such a way that they can retain their structural integrity even at boiling point of water. But you cool them down, they're going to lock up and they're not going to work at all. So they're going to basically freeze at what's body temperature for us, or maybe at room temperature, depending on, every microbe has a different, every microbe's curve is going to be slightly different. Every species is going to have its own unique curve. But thermophiles are going to lock up at room temperature or body temperature, and their enzymes are going to work perfectly at a pretty hot temperature. And then in terms of their plasma membranes are going to be structured out of a lipid that's a little bit more like butter, right? It needs to be hotter in order to be fluid. You bring it down to room temperature and it's going to lock up, it's going to solidify and not have that dynamic quality that it needs. Okay, so different microbes have different enzyme structures and different plasma membrane lipids that are going to allow them to function at their own ideal temperatures. Now, what might the human body, the microbes that inhabit your body, be they mutualists or pathogens, they're going to be mesophiles, right? They're living in a mild temperature. This is about 37 degrees Celsius. That's about body temperature. That's a mesophile. Optimum temperature is 37 degrees Celsius. That's body temperature. That's a pretty mild, moderate temperature. So anything inhabiting your body, any microbe inside your body, loves moderate temperatures. They are mesophiles. Their enzymes work best at body temperature. But if you're going to talk about a bacteria in a hot spring, those are going to be thermophiles. And this is why commercial sterilization and pasteurization are not designed to sterilize food. You don't need to sterilize food. You just have to kill off the mesophiles, because it's the mesophiles that are going to invade your body, right? Anything infecting your body, good or bad, is a mesophile. A pathogen that likes to live inside you, it's a mesophile, because you are a moderate temperature, right? So when you pasteurize something, or when you use commercial sterilization, you're not sterilizing it at all. You're not getting rid of all the microbes. That's why milk will still go bad in your fridge. You can just open it a crack, close it again. No new microbes have gotten in there. You leave it in the fridge long enough, it's still going to go bad. That's because there are microbes in there. They're just microbes that are not pathogens to you. they might be thermophiles or something like that, right? And so this allows you to retain more flavors and nutrients in the food by not heating it too much for too long. If you heat it for just a little or for a short amount of time, you might have plenty of thermophiles remaining, but those are not pathogenic to you because they don't grow well at human body temperature. The concept is very similar with compost. If you are using this compost to grow vegetables that humans will eat, it's important to kill off the human pathogens in a compost pile. And you do this by letting the mesophiles generate enough heat that they kill themselves. Mesophilic bacteria generate heat as they metabolize, just like you do when you exercise. All the heat of the mesophil metabolic activity eventually makes it too hot for the mesophils that started there. So the mesophils, they're metabolizing, they're making it hotter and hotter and hotter. Eventually they make it too hot for themselves. The mesophile enzymes denature, the mesophile cell membranes melt, and the mesophiles die. But the thermophiles have seeded as it got warmer, and they are now quite happy in the new hot environment. And the thermophiles continue metabolizing and generating heat, making it hotter and hotter and hotter, keeping the compost pile too hot for anything that could be a human pathogen. Actually, if you care for your compost correctly by keeping it oxygenated and keeping it the right size and the correct moisture content, you can generate enough heat to heat barrels of water and use the hot water for showers, for example. And actually in this image, the farmer is actually capturing methane from the compost. So these barrels, there's bacteria that produce methane in here, and these barrels are capturing that methane. He's going to use methane as a fuel for activities on his farm. But the problem is this compost gets so hot that it could explode the methane. So to keep the methane cool so that it doesn't explode, he runs these hoses around it, runs cold water through the hoses. The hoses pick up all the heat from the methane, and that makes the water hot. He runs the hot water away to the hot showers on the farm.